Welcome back to 6.3 where we're dealing with periodic trends. So far we've taken a look at the trends in atomic radius and ionization energy. And again, the whole key to understanding these trends is really looking at the strength of the nucleus and how far away the electrons are from that nucleus. The last trend that we want to take a look at is what's called electronegativity. And electronegativity is simply the ability of an atom to attract electrons. There you go. Oop, I should say attract. Having a little issue there. Attract electrons when the atom is in a compound. Alright? Now what do we mean by that? Well, let's just say, looking at this table down below, you can see all the different electronegativity values. Let's say we have an atom of hydrogen and we have an atom of boron. I'm going to make boron a little bit bigger than the hydrogen. Actually, it's quite a bit bigger than the hydrogen. What happens is these electronegativity values tell you the relative ability of that electron to attract the electrons. Now, because they're almost the same, the electrons are going to pretty much stay with their respective atoms. All right? So there's really not going to be much of a shift in the electron density, and effectively the electrons will be equally shared. Now, on the other hand, if you have something with, say, fluorine and sodium, okay, sodium is going to be about, let's just say, this size, while fluorine might be something like this size. The fluorine has a very high electronegativity compared to that of sodium. In fact, fluorine is the most electronegative element. What that means is that though the sodium has more electrons, it's actually going to be, those electrons are going to be drawn towards the fluorine atom. And so if I redraw this, if this is the nucleus of the sodium and this is the nucleus of the fluorine, the electron density is going to be shifted very much so toward the fluorine. The fluorine is much more electronegative, and the electrons are going to spend more time around that nucleus. All right, so that's in a nutshell what electronegativity is. It's how able the atom is to draw the electrons towards it when it's in a compound. Now, let's take a look at the trend. If you notice, as you go from left to right on the periodic table, and of course these elements are set up in the same order as on the periodic table, you'll notice that electronegativity, En, increases. On the other hand, as you go down the periodic table, electronegativity decreases. Now, why is that? Well, again, it goes back to the strength of the nucleus and the relative distance of the electrons from that nucleus. As you go from left to right, all the electrons are in the same energy level, but the nucleus is getting stronger and stronger. So in row 1 here, or actually it's row 2, fluorine has the strongest nucleus of this group. Alright, so it's going to attract the electrons closer to it. In fact, that is why the fluorine atom is the smallest one of that group. Well, the reason why the fluorine atom is the smallest is the same reason why it can attract the electrons towards it when it's bonding. It has a very, very strong nucleus. Now, conversely, you might be thinking, well, as you go down the periodic table, the nucleus does in fact get stronger, and it does. But what happens is that the electrons get further and further away, so two things occur. The electrons are further away, so they feel the nuclear charge less and less, number one. And number two, the more electrons you have in the atom, it starts to shield, what they call nuclear shielding. It shields the effect of that nucleus from the outer electrons. Let's try to illustrate this. Here's your fluorine atom. It only has 2 energy levels, the first and the second energy level. Alright? When you get down to, say, iodine, iodine is in the 5th row and has 5 energy levels. Okay? It's a much bigger atom than fluorine. So again, we'll label this fluorine, this is iodine. If and let me change colors here just so we can see what we're saying. If this nucleus of iodine, though it's very, very strong compared to that of the fluorine, if this is going to attract, say, an electron that's way out here, number one, the electron is very, very far away from the nucleus. Plus, it has all of these electrons in the way. And so that creates what this shielding effect does. It shields the nucleus from that electron. So even though this nucleus is very strong, this electron cannot feel its pull very well. On the other hand, if we stick an electron right here next to fluorine, though this nucleus is weaker than that of iodine, it's a relatively strong nucleus, and it only has just a few electrons between it and this outer electron. So it actually has a very, very strong capability and ability to draw that electron towards it. All right. So again, the whole idea here is how well these things can be attracted towards the nucleus, and it has to do with the two things: the strength of the nucleus and the shielding of the electrons. Fluorine is the most electronegative element because it has a relatively strong nucleus and few electrons between it and any electron that it would try to attract. And so it therefore would have the strongest electronegativity. On the other hand, cesium down here, cesium has though it's actually a fairly strong nucleus, it's in the same boat as iodine, where it is such a large atom. If I can scroll down here and create a little more space, all right, it is in the 6th row, and so it's actually even going to be bigger than iodine. There's 3, 4, 5, 6. It gets very big. And so while this is a relatively strong nucleus, the electron is so far away it virtually has no ability to pull that electron towards it. And it has the lowest electronegativity. Alright? So, in the next podcast, our last podcast of this chapter, we're going to summarize all of these periodic trends for you and then call it a chapter.